Hi, so this is the start of my ELEC351 demo. I'm just going to run through the functionality of my code that I'm handing in and how it aligns with the requirements set out in the coursework specification. We're going to run through each requirement kind of one by one, adding detail where I think is necessary. So, starting in my main file, the code adds in all of the header files that I've used, so all the code has been split into what I believe to be the necessary header files. So we have the University of Plymouth header file embed library, and then we also have my measure data button handler and the terminal libraries brought in that I've created. So the first requirement of the coursework spec was to sample the data every 10 seconds. This sample included the temperature, pressure, and light level, and this is done in the, so initially this is the main function starts a thread called sample thread set to OS priority real time, which I believe to be the highest priority thread on the support board system. This sample thread is then has a sample data function attached, and this is used with the callback function to feed in a sensor data struct, which is initialized just above on line 37. So if we enter into measuredata.cpp, which is where the sample data function is, we'll see that the sample data function takes the sensor data struct by reference, meaning that we have to be careful with what we are doing to that struct here, which you can see in mutex, which I'll explain later on. So this struct sets up, once it's initially entered as the thread's initialized, it sets the variable sample num equal to 1. This is used to just identify which sample we're currently on later on when we're writing to the SD card. This function then enters a loop which initially requires a semaphore. Now, the code will wait here until the semaphore is released by this timer. So I've attached a ISR to a ticker, this sample ticker, which is initialized at the top of main. This ticker calls this interrupt service routine every 10 seconds, and this service routine will just simply release the semaphore. So once the semaphore is released, the code will continue, and what will happen is it will read a flag called sampling enabled. So this flag is atomic, so we need to use the load function of the atomic class, and this is just ensuring that it can't attempt to read this value when it's in the middle of being changed elsewhere in the code. So this flag will get changed by one of the terminal functions, which again I'll explain as we go on. So when sampling is enabled, which it is by default, we retrieve the time of the system using the time function, and then we will also lock the sample mutex to make sure it's not being read elsewhere, and read in the temperature, pressure, LDR or light reading, and also store the sample num in that struct, as well as copy the current time as a string into the timestamp variable. This sensor data struct is set up in the H file and is defined as shown on line 17 to 23. So once the data has been copied into the struct, we use a try alloc on the mailbox to allocate space for a mailbox item. This mailbox has been set up in also in measuredata.hpp as an external variable. This mailbox is used multiple files throughout the code and potentially multiple threads. Mailbox is inherently thread safe, so this is not a concern, does not need a mutex or a semaphore around the mailbox. You can see we've told it to take it's creating a mailbox of the type data, which is the struct we just defined, and it's taking six of these objects. This can be changed easily up here using the define macro. So we have a safety check to ensure that the data, the space in memory has been allocated by the mailbox, and if it has been allocated, we enter into this if statement and we copy our readings into that space in memory. Then we put this line puts the data into the mailbox, and then if successful prints out the readings to the terminal, as you can see currently on reading 218, and then increments the sample number. If the mailbox can't put the data in, it's a sign that the mailbox is full, so we print out to the operator that the mailbox is full and we free the attempted allocated space to ensure we don't leave any wasted memory behind. If the current data is equal to a null pointer, it means the mailbox has failed to allocate the memory, so we state to the operator that the mailbox failed to allocate the data, and we just skip that sample. Down here you'll notice there's a flag called new sample equals true. This will be explained later on. So that is the sample function, and again that was called every 10 seconds and runs in the highest priority thread. That is the only function that runs in the highest priority thread. So after the sample thread, we also have the terminal thread. So I'm just going to reset the board quickly. So as you'll see, at the moment we're getting the message no SD card detected. So I'm just going to remove the SD card from my laptop. I'm going to now reset the board once more, and you should see the message that it's writing to the SD card as it boots up. And setting off the buzzer, which we will turn off. So when the program first boots up, we're also going to, in the main thread, we're just going to, actually no, not in the main thread, in the SD thread, which is initialized in main, we start the SD handler function. We attach that to the SD thread. This thread is set to the default priority, and within measuredata.cpp, this handler will initially write a header to the SD card. What this will do is wipe the SD card and write a simple header to it just saying sample data. Here you can see that that header has been successfully written, and a message is displayed to the operator when that message is successfully written. After that point, this handler goes into a while loop that polls if the mailbox is full or if the flash command has been sent to the terminal. If the mailbox is full, all that is true, it goes into the empty mailbox function and sets the flag that ensures that the SD flushed flag is reverted to false if the flash command has been called. So it's worth noting that this handler also has a sleep for in it. It sleeps for 1 second. This just stops this function from polling continuously, as it's a waste. The sampling will only fill up the mailbox every 6 seconds, and flushing to the SD card, although needs to happen relatively quick, is not time critical. So just to save some power, we are sleeping this thread for 1 second every time it polls. So within the empty mailbox function, what we do is we set up the following: we set up the count variable, we set up the output buffer and output string. So to prevent damage to the SD card when we write to the SD, we want one large SD write. So we iterate through each item in the mailbox, making sure we stop either when it reaches empty or when the count is less than the mailbox, or it iterates while the count is less than the mailbox and while the mailbox is not empty. We try and allocate memory to sample, again doing the same safety checks as before on whether the mailbox successfully allocates memory. And if it does allocate that memory and retrieves the item from the mailbox, we build a string in human readable form to present to the SD card, and then concatenate this string into a large buffer. This buffer is the mailbox size times the length of the string. This would be adjusted. If you upped it to 60, this buffer could get large, potentially cause memory issues. But for now, we're using 6 samples, which means the SD card is written to every minute. And then the count is incremented. Once the mailbox is emptied, we write that output buffer to the SD card. And a message will be displayed if that has been successfully written. It should say successfully written to the SD card, and will also say mailbox emptied once the program returns to the empty mailbox function, or once it returns to the SD card handler function, it will also state mailbox emptied, as seen in the terminal down there. So the reason that it was put in a thread is that the SD card writes are slow, so it's got its own. It's been buffered twice. It has the FIFO mailbox buffer and also the string buffer. The mailbox is thread safe. The string buffer is used nowhere else, so it's also safe. And then the thread just means that it doesn't block any other operations. There are also upper and lower thresholds, as you heard the buzzer go off earlier. Thresholds are currently set to be okay in labs, not necessarily in my room. So turning this on, not going to turn the buzzer on now, but it turned it on earlier. If I enter into the terminal to select L, and then cover up the LED. After 10 seconds, a new sample will be taken, and it's still not going to set the buzzer off, but it will do when it exceeds the limit. I'm just not able to do that right now. Turn that back off. So that program happens down here. So if it exceeds a light level of 0.85, it will play that tone, I believe, when I have my finger over it. It did not exceed that limit. Or I believe that turning off the buzzer halfway through the program will make it fail. So if I turn it on and just reset the board, that buzzer should now go off on the first sample. It's not going to play ball. I'm going to change the light level. and the buzzer's no longer working. But it worked earlier, so I'm going to move on from that one, and I can promise that it does work. So there is an upper limit and a lower limit, upper limit and a lower limit, and then lower limit, upper limit here as well. The reason for no hysteresis is that the sample only happens every 10 seconds, so there would be no buzzer jitter due to such a slow sampling rate anyway. So I believe this is fine. This function is called every time the LED strip updates. So, and this happens within the main thread as, again, not a time critical operation, and fits within the main thread perfectly. So to avoid these functions blocking each other, a lot of these functions, none of these functions have blocking capability, and they're in the main thread. Then I've purposely kept the sensor alarm and the LED strip, which I will talk about in a second, outside of the highest priority thread, to mean that that highest priority is blocking for as little time as possible, and that semaphore release in the highest priority thread means that no other programs are blocked. With a separate thread, we have a separate thread for the sample, the terminal, and the SD card, with also technically another thread for the main. This means that all the threads get run sequentially by the real-time operating system, and no program should be blocked. It's all called sequentially, so there shouldn't be any race conditions for any values, and any values that could occur in, as shown in measure data, had a mutex around them. And any flags that we set have been set to atomic, so these flags inherently will not be interrupted and are safe to use in multiple threads. In terms of spin locks and busy loops, I believe that anywhere that I have a busy loop, I've put a thread.sleep in, as shown in the SD card busy loop. The only one that doesn't is the terminal. The user is potentially going to be typing into the terminal at any point, and we don't know when that is. So this sits in a while loop and will sit within this get line is blocking, but the terminal has its own dedicated thread, so it's only blocking itself at this get line. It is sitting at that point, potentially busy waiting. However, I believe this is necessary in this case. The user wants an instant reaction from the system when they type something in. So the terminal can do all the functions asked by the coursework spec. So it enters into the terminal thread. This function is attached to that thread, and I've used POSIX style regex, although this one I've left a comment in there to state that this isn't the nicest regular expression to look at, but what it does is it matches the word date time, then matches 2 digits for the day, 2 digits for the month, 2 digits for the year, and then so on for 2 digits for the hour, minutes, and seconds. These are then copied into the DT matches object and converted back into a TM struct. This struct provided to us by the time class or the Plymouth library. Once this function gets called, so we'll give a quick demo in the terminal. So date time 9, 9, 9, 9, 9, 9. You'll see that we get a message saying the date time has been successfully updated, and the command that I put in has been echoed back, so I changed it to the 9th of September 2009, 900 hours, 9 minutes and 9 seconds. We can also see that proof that this has been updated properly. You should be able to see just about that the time on here, if I cover up these, time on here has been updated to that date, proving that that function has worked. And also, so this time editing flag just makes sure that when in main, which is where the LCD gets updated as well as a non-time critical operation, if the time edited flag is true, the real time operating system is updated to be that time, and then this will then follow suit and use that time instead. Additionally, in the terminal.cpp, we have the flush command. So now we are not at, the mailbox is not full, I can type in flush, and it will flush the buffer TSD card, tell us that it's successfully written, and then within a couple of seconds should take the next sample and continue on as normal. The mailbox will now be empty, so it will take another 6 samples. This sets the flag to true, just so that the SD thread is aware that the flush command. So my video cut out last time, so I'm going to continue from where I left off. I apologise if I go over anything again. I can't exactly remember what happened as my video was corrupted. So here I believe I got to the datetime. So this is a regex expression, a POSIX one, that matches the 2 days, 2 months, 2 years, and also 2 hours, 2 minutes, and 2 seconds. This gets put into a matches smatch object, which then can be used to retrieve all of those matches and update a TM struct, which is part of the, I believe, the Plymouth library, and then or the time library, and update the global now variable. And then we also set the atomic time edited flag mentioned earlier to true. Then in main, once the main thread, the main loop gets to this section, if that time edited flag is true, the RTOS time is updated and that flag is set to false. This will also happen with the buttons. So I will give a quick demo in the Nucleo console. As the board resets. I think we're going to have to create a new console. New serial monitor. If I quickly press. There we go. So now if I type into the terminal date, time, 09, 09, 09, and 09, 09, we can see that the time's been updated, and if I now cover up this LED strip, you can also just about see that the time on this LCD is the 9th of September 2009, 9 hours, 9 minutes, and, well, no longer 9 seconds, but it would have been. These can also be updated with the buttons, which I will run through in a minute. So at the moment the default setting should be seconds, so if I press A you can see that the seconds is jumping up. If I use C, the seconds will decrement and go the other direction. If I use B and D, if I use B, I can now change to the minutes. So you can see that the minutes is now going up. If I press B again, I can change the hours. If I press B again, I can change the year. If I press B again, I can change the month. And if I press B one more time, I can change the date. And then that will wrap around back to seconds, but I can also use D to go the other way through the time frame. So that is the time and date selection. So then once we go through that, So once we go through that section of the terminal, we are now at the flush function. This function will flush the current contents of the mailbox, whether full or not, to the SD card. So if I type flush in the terminal, I've spelled that wrong. We can see that we get a nice little message showing that the buffer has been flushed to the SD card and that it's happened successfully, and then also that the mailbox is emptied and the samples will continue. So that flush, although called here, sets an atomic flag to true, and then that flush command will just call empty mailbox in the SD card thread, and that will happen in its own thread in the background. If the match aligns with, if the regex matches select and then also matches alpha character within square brackets, if that alpha character is T, it updates the LED strip to display the temperature. If it's P, it displays pressure on the LED strip, and if it's L, it displays light level. So you've already seen that, I believe. And if I type select L, you see that it's now displaying light level on the LED strip. When the next sample comes in, that will update the LED strip. If I change it to select P, it's now displaying pressure on the LED strip. If I do mess that up, and I put in some random value like I, it will tell me that's an invalid choice and tell me what the choices are in between the square brackets. Terminal will also, if I type something in random, you already saw it flush, it will tell me what the correct functions are. It will give me a little help statement. As well as that, we also have, and it changes the flag. So the way that is handled is it changes the display param atomic flag from either 0, 1 or 2. 0 referring to temperature, 1 referring to pressure and out, and 2 referring to the light level. This is atomic, so if the main script and then the light level script, the terminal try to read or edit this at the same time, there should never be a conflict there. So as well as that, we have sampling, so we can turn sampling off. Like that, the sampling can be disabled, and no more samples will come through. And this isn't blocking, so you can still type in other commands. You can still change the date time. So if I do that quickly, if I change it to 10, 10, 10, 10, 10, 10. You see that that's updated, and that has also updated on here. If I cover up the LEDs for you, there we go. You can also see the 10th of October 2010. So then we can be free to just turn that back on. I've turned it off again. Good job, me. I go sampling on. So that's the terminal, and again that happens all in the dedicated terminal thread, so that does not block. It blocks itself with this get line, and that just means it rapidly responds to user input. The get line is not affected by the print statements happening in different other threads either. So if a print to the terminal happens at the same time as the user is inputting something, that their user input is not affected. So in terms of mitigating against deadlocks and thread starvation, I don't have any blocking functions or any non-atomic global variables that should cause an issue there. I have the sensor data in measure data inside of mutex. Although this mutex is not used anywhere else, so it should never struggle to get access to it. As well as this semaphore is only used in one place, so it should always acquire it, and it should never deadlock or be thread stuffed. Like I said, all flags are global, all flags are atomic, and then everywhere else is controlled sequentially, either through an interrupt or just sequential program. So to my understanding, no critical errors can occur, and I've tested down to a 10 millisecond sampling time and the code runs fine. So we've already looked at the LED strip, making it hard for you to see the LCD. LED strip updates every time the sample updates, so we talked about the flag new sample equals true in main. When that new sample goes to true and the while loop reaches it, the LED strip is updated using a copy of sensor data. As it's a copy, it should be thread safe. So you'll see that we've initialized an LED strip object, so as required by the coursework spec, the LED strip class has been developed as an API. So if we head into the LED strip.hpp, we can see that we've got an LED strip class. We've got some private member variables and also some private member functions. We have measurement LED val, which takes the current measurement value, takes an upper limb and a lower limb for what is considered 0 on this LED strip and what is considered 24 on this LED strip, and then converts that measurement to be somewhere in that range. Then we have display LED, which just takes the value returned by the previous function and just displays it on the LEDs. We have a public constructor, which takes the number of LEDs, so if you did only want to use the first 16 you could, but we've stuck to 24 for this demo. And then the main function update LED strip is the only one you would need to use elsewhere that just calls all the private functions and handles the LED strip. So if we have a look at that quickly, see the constructor just takes the number of LEDs and then stores it, copies it into the private variable. We have update LED strip, which first, this is where the sensor reading alarm is triggered and checks to make sure if there are any thresholds. We've already discussed what that function does in the earlier requirement, and then switches depending on the atomic flag, so display param, if that flag is 0, then we're going to display the temperature and we're going to convert the temperature to be between 15 and 30. If it's lower than 15 or higher than 30, it will always be 0. If it's higher than 30, it will just become 24. It will just max out the LED strip. Then the same for pressure, with slightly different lower and upper limits, and the same for light level. Once the LED strip's been updated, we set a new sample back to false, as we no longer want to update the LED strip. So measurement to LED val, like I said, normalizes the values to 0 and 24, but how it works is it converts it to a range between 0 and 1. If it ends up less than 0, it means it was outside your range and then gets rounded back up to 0, or if it was bigger than 1, it means it was also outside your range and just gets rounded down to 1. This is then converted to an integer value between the 0 and 24, and then using base 2, so 2 to the power of 24, take away 1, will give you the binary value that would max out all these LEDs, and then the same logic works for each value in between. We then have the function display LED value, which just writes to the LED strip, using a bit shift to take that 24-bit number and split it into 3 separate 8-bit numbers for the red, green, and blue sections of the LED strip. Additionally, we discussed it and I showed it to you, but the button handler all happens in its own file. These are based on the interrupt in class. This interrupt in class allows you to attach a function to the falling edge of each button, which is what I've done, and at the start of main I call this attach button interrupts, and we enable all the interrupts as soon as possible. So then when a button is pressed, the interrupt is disabled, stopping you from being able to press it again, and a debounce timer is attached with 100 milliseconds for debounce. We'll have a look at what that function debounce A does in a second. So we increment the current global time variable by epoch values selected time frame. So in this epoch values, we have the epoch value for a day, a month, a year, and then an hour, a minute, and a second. And then we have the default. Here we have the default selected time frame, which is seconds. So 0, 1, 2, 3, 4, 5. So the default one is a second, but using the button B and button D, you can change that selected time frame from 0 to 5. Then we set that the time has been updated flag to true, which is atomic, so it's thread safe. Once that's been set to true, again in main, the time of the RTOS will be updated. You see the debounce functions. All these do is after 100 milliseconds, the button interrupts get re-enabled and the timers get detached. So this will not be called until the button is pressed again. And that is it for the buttons. In terms of suitably structuring the whole program, everything's been split into CPP and HPP files to keep it nice and tidy. All functions are in their relevant files. If there are functions from one thread are attempted to be kept together, and my naming convention, I've kept the same as much as possible, other than variables such as tm_midday, which comes from a struct that I didn't create. As well, in my header files, I have header guards, and I believe everything is suitably commented and also suitably indented for easy reading. I've added my student number and name at the top of every file, and hopefully made it as easy to read as possible. I think there's a few elements I haven't covered in main, so just to run through the main finally. It attaches the button interrupts, LED, enables the latched LEDs, updates the system time to the global variable now, which is initialized as this epoch value. Initializes sensor data, we've discussed that, and then once it gets into the wild true, it updates the 7th segment with the current night level. Then also, if a new sample comes in, updates the LED strip. If the time's changed, updates the time, and then after that, it converts the time into a TT, which can be written to the LCD, which is why the LCD updates in real time. And to stop a visual effect of the LCD updating too fast, we add a small 5 millisecond delay in main. And I believe that is it.